So let's get started. Let me introduce today's speaker. Yesterday, I sent Yang email to ask for his bio, and he sent me 2 sentences. He sent me 2 sentences. One is Yang is an assistant professor at Cornell Stat, and he graduated from Johns Hopkins. That's it. I think he is too humble because he has many publications, and he also received very prestigious awards, including the 2020 NSF Career Award. I think he wants to keep the introduction very short and spend more time on the research topic. So without further ado, let me hand this over to Yang.
Okay, let me share the screen. Okay, so can everyone see the screen, right?
Yes.
Okay, so thanks for the invitation and the introduction. So it's my great pleasure to be here and share some of my recent works. And so today I will mainly talk about the estimation in multivariate response regression with hidden variables. Okay, so this is the joint work with 2 Cornell students. So Mike Bing, and he will join the University of Toronto statistics as assistant professor in next spring, and also like another student, Sally Xu from Cornell. Okay, so question, yeah, okay. So here is the motivation of the talk. Okay, so in this talk we focus on the association analysis. Okay, so in the next few slides you may see some examples about causal inference. Okay, but the main focus on today's talk is still association analysis. So that causal inference is just to connect with some maybe literatures. Okay. Okay, so in association analysis, so the goal is to estimate the association between a set of observed feature X and the response, a set of response Y. So here is an example. So the genotypes is our X, usually it's very high dimensional. Okay, so the Y is the phenotypes, which is often multi-dimensional. Okay, so maybe the dimension is not that large compared to the sample size N. Okay, in this case. Okay. So in association analysis, one important problem is to control for the confounding variables, right? So if we can measure those confounding variables, we can just throw them in the regression models, so we can adjust for those confounding variables to estimate the association between X and Y. Okay. However, in practice, some of the confounding variables may not be measurable, or they may not be collected, say, due to cost constraint or some ethical issue. Okay. So what happens if there exists some unmeasured, or we call this hidden confounding variable, just called hidden variables. Okay. So the goal of today's talk is to deal with those confounding variables, the hidden confounding variables in multivariate regression problem. Okay, so let's first look at some simple examples. So here is a very simple example. The Y is different type of tumors like lung cancer, breast cancer, etc. So the X is the, for example, the risk factors like alcohol use, etc. And some of the confounding variables, say smoking, is very easy to measure. So we can also put this smoking variable in the regression. Okay, but there may also exist some unobserved demographic variables. Okay, so in this talk we use variable Z. Okay, we use variable Z to denote the hidden variable, or unmeasured variable, or latent variable. Okay, so they all mean the same thing. Okay. Okay, so in the second example, we see a DAG, okay? And we know in the causal inference, if we impose some additional assumptions on the DAG, so those errors in the DAG can be interpreted as the causation, okay? So let's say if I have this DAG, so I have, again, a response variable Y. So these are the, for example, the multiple clinical outcomes. and my X is here, this genotypes, the SNPs, okay? And I may also observe some other covariates. So these are the measured covariates like age, gender, etc. Okay, so I can also put them as a subset of X. Okay, this is also a part of X. Okay. So in this stack, you see there's another variable here. It's called intermediate phenotypes. Okay, so in the causal inference literature, so people call this variable as a mediator. Okay, so for example, here you can say, okay, if we think about this in the causal structure and the causal effect of the genotypes, okay, on the response, the clinical outcomes can be decomposed into two parts. So one is this arrow is the direct effect. So the other arrow is here that goes through this intermediate phenotypes to this outcome. So it's called the indirect effect. Okay. So if those intermediate phenotypes, okay, are observed, okay, so we can collect all those variables. Then we can use the existing, say, the causal inference methods to estimate both direct effect and the indirect effect under some conditions, right? Okay. However, if those intermediate phenotypes or some of those variables are unobserved, okay, then it's kind of unclear whether we can still estimate this direct effect and the indirect effect, or even whether those two effects are still identifiable, right? It's unclear. Okay, so those unmeasured variables makes the problem much more difficult. Okay, now let's briefly review some existing methods that deal with hidden variables. Okay, so the first class of method is called the surrogate variable analysis, the SVA. So it is developed by a group of biologists or biostatisticians. I think the first paper is by Jeff Leake and John Story in 2007. So I remember when I was a PhD student, Jeff Leake gave a job talk at Johns Hopkins. So this is basically his job talk, if I remember correctly. Okay, and also there are some more recent development, okay, on this method. So this SVA is very popular in genomics data. Okay, so basically they consider the following setting. Okay, so the Y is the gene expressions. Okay, so it's dimension M. So usually the M would be very large, right? Okay, the gene expressions. So the X is a very small, it's a very small set of variables. So for example, it could be just a treatment variable, it's treatment or control. So that's why I say the X is in R. So if you have very low dimensional X, you can still use this SVA, I think. Okay. And the hidden variable, as we said, we use Z to denote the hidden variables. Okay, so this represents the unmeasured or unobserved technical factors like a batch effect or some biological factors like cell composition. Okay, so these are the unobserved variables. Okay. So the model to consider is this linear regression, right? So Y account for both observed variable X and also hidden variable Z plus some noise. Okay. So there are a variety of methods that estimate those parameters. So some of them are quite heuristic. And as I said, there's a more recent, like rigorous treatment on this problem. Okay. Okay, so this is the first class of method. So the second class of method is called structure equation model with hidden variables. So you can say you have almost the same model. You have essentially the same model, but okay, in the structure equation models, we will further impose some causal structure among X and Z. Okay, so there are two possible models for that. So one is the mediation model. So basically, you can assume X is a cause of Z. So that's why I have this arrow. So X is a cause of Z. So this is the case, for example, in this example, I have X, I have Z. So the X is a cause of Z. Okay. Okay, so this is the mediation model. So another model is called the confounding model. So basically we say, okay, they should be a cause of X. Okay, so we flip those arrows in some sense. Okay. And both of these models have been recently studied by those authors with hidden variables. Okay. But usually they need to know, okay, either I have this mediation model or I have this confounding model. Okay. So I have to know this to use the method. Okay. So although both of those like methods enjoy great success in their fields, okay, so there are several limitations of those approaches. Okay. So for the SVA, so we know SVA is only feasible for small p. So what is a p? So the p is the dimension of X. So here p equals 1. Okay. So if p is not 1, it's 2 or 3, you can still use that. That's no problem. Okay. So, but it should be small. So p is very small. And also m, so the dimension of y should be very large. So they assume the m is much larger than the sample size n for some technical reason. Okay. But in practice, I would say m or p, or either m or p, they could be large or small compared to n, depending on the applications. So in the first example, if we have these genotypes and phenotypes, so usually genotypes is very high dimensional. So the p would be very, very large. But the phenotypes, say the m, maybe is 10 phenotypes. So usually is smaller than n, or is maybe in the order of n, some sense. Okay. Okay. So it depends on the applications. Okay. So for the structure equation model, okay. So you can say the structure equation model heavily depends on this causal, these two causal models. Okay. So first of all, you have to impose some causal structure between X and Z. Okay. However, in this case, our Z is unobserved, so it's really hard to impose the causal structure between X and some unobserved variable Z. So I don't really know if Z is the cause of X or X is cause of Z. Okay. In addition, they usually require this linear causal structure. So you can see these are the linear structure, right? Okay. So this is also quite restrictive. Okay. And also it studied the univariate y, but here, okay, we want to make the y study the case that y is multidimensional. So this actually gives you a lot of benefit, you will see later. Okay. And also we want to make the dependence structure among between X and Z flexible. So that Z and X, they can be correlated in an arbitrary way. So we just say, okay, X and Z are correlated, that's it. We don't really need to know, okay, they have any causal structure or they are linear or it's not. Okay, okay, so this for the structure equation model. And also another challenge is if we consider this model, so because Z is unobserved, right? Z is unobserved. So it is unclear whether this regression parameter psi is still identifiable or not based on the data X and Y, right? So the identifiability of psi is unclear. Okay. Okay, so now let's formally lay down our model. So this is, we consider basically the same linear regression model, okay? And the y is an m-dimensional response vector. The x has dimension p. These are observed features. And z is the k-dimensional hidden variables. Okay, so we do not need to know the value of k. Okay, but we need a way to kind of select k in the end. Okay, so for identifiability, we need to assume k is less than m. Okay, k is less than m, and the e is just some random noise. So our goal is given n ID copies of data X and Y, there's no Z because Z is unobserved. So we want to estimate the association between X and Y. For example, this psi or something related to psi. Okay, so this is our goal. So what's new today? So in today, we will discuss the identifiability of psi and also a new identifiable target. And we will propose an algorithm, okay, called hidden variable adjustment estimation algorithm. We call that HIVE. okay, to estimate the parameter. And also we establish the theoretical result, the consistency and the rate of convergence for the estimate in high-dimensional models. And we extend our method to the heteroscedastic case. Okay, so let's start from the identifiability. Okay, so to show the parameters identifiable or not, so we basically use the following strategy. Okay, so let's first do a L2 projection of Z onto the linear space of X. Okay, so that is this equation. So this is a Z, and this is A transpose X. Okay, is on the linear space of X. And Z minus A transpose X, we call this as the W. Okay. Okay, so this is the definition of A, and we treat this W as an error. Okay, so in this step, okay, we do not require X and Z, they have linear dependence, right? So no matter what they are, how they depend on each other, so we can always do this L2 projection, okay, and on this linear space of X. So this does not pose any model assumptions, etc. Okay. Okay, so with this decomposition, okay, we can rewrite our model. So this is our model, right? Okay, we can rewrite our model as follows. Okay, so we combine those A and B, the product of A, B, and this psi together. So this is a coefficient of X, and also the rest of them are the errors, right? Okay, the rest of them are errors. And so we can say, okay, if we have these hidden variables and we do just a regression y on x, then what we can recover is this psi plus A times B, okay, rather than psi, right? Okay. So in general, this psi may not be identifiable unless we can find a way to separate these two matrices. Okay. So the question is, how can we do that? How can we separate these two matrices? Okay, or if possible or not. Okay, so the way we make the parameter identifiable is the following. Okay, so let's further introduce a projection matrix. So this is a projection matrix PB on the row space of B. Okay, so this is the B, right? Okay, we consider a projection matrix on the row space of B. Okay, and we decompose our parameter psi into two parts. So psi times PB complement, we call the theta, and also psi times PB. Okay, so I further decompose the psi, okay, parameter into two parts. Again, I will plug in my models and say what I can get. So if we plug in models, and again, I make this as a first term, theta transpose X as a first term, and I put psi PB and the product of AB together as a second term. Okay, so I have these two terms, right? So here I say this theta transpose X is the effect of X on Y that cannot be explained by the hidden variables. Okay, so similarly, for the second term, I would call this as the effect of X and Y that can be explained by the hidden variables. Okay, so why this part can be explained by the hidden variables? The reason is so this matrix is in the row space of B. So in other words, if we look at the previous, our model, right? So this hidden variable Z is unobserved. So mathematically, it could be anything, right? Okay. Of Z is still a Z hidden variable. Okay, so in some sense, this second part, okay, so this second part, okay, can be written as this B transpose Z for some suitable Z. Okay, so we call that as we treat that as a latent variable. Then this second part would not be able to identify it. Okay, so this second part, okay, is the effect of X on Y that can be explained by Z, so it's not identifiable. Okay. And so in the mediation analysis, we can treat this as the theta transpose X as the partial derived causal effect. And indeed, we can show that this theta matrix is identifiable. Okay. So this is the result in the next slide. Okay. So we can prove that okay, theta is identifiable. So again, this is our model. I just rewrite it. Okay. So here I have a sufficient and necessary condition for identifying the parameter theta. Okay. So this result is very simple. So here I first focus on the homogeneous case. So the covariance of E, assume the covariance of E. So this is the error E equals tau squares times the identity matrix. Okay. So it's homogeneous case. Okay. Homogeneous case. So in this homogeneous case, okay, we have very simple identifiability result. So it says theta is identifiable if and only if the covariance of W. So what is W? So the W is the residual from the projection. So this is W. So that is a k by 1 vector, okay, the k by 1 vector. So we assume the covariance of W has full rank with rank k. Okay, then we can say theta is identifiable. Okay, so this is the identifiability result. And I will show you more details later, but the key idea in this identifiability is to use this noise structure. So here I emphasize, okay, this is my noise epsilon. Okay, so if you look at my noise epsilon, so you can say it actually has a factor model structure, right? So you can treat B as a loading matrix, W as a factor, so E as a noise. So you can compute the covariance of this epsilon. So it has this formula, right? And if this is the homogeneous noise, then we can use this to identify the right singular space or degenerate the right singular space of B, right? Okay, so we can use that to identify the right singular space of B. So from the right singular space of B, we can identify the projection matrix PB. Okay, so that is actually the key step in this identifiability proof. So of course, you may say, okay, this homogeneous noise is very restrictive. And in practice, for example, different clinical outcomes, they may have different variability, right? So we can also relax this homogeneous assumption to the heteroscedastic errors. Okay, so basically the covariance of E is a diagonal matrix, but with tau 1, tau 2, and tau n, okay, an equal variance. So we can extend our method to this case as well. Okay, so so far we have seen, okay, the theta is identifiable, but the question is, okay, if I have this linear regression problem like here, my parameter of interest is psi, right? Okay, so this is my regression coefficient. So I'm interested in psi. Okay, so can I say anything about psi? Okay. So the answer is yes, but we need some extra conditions. Okay. So again, this is our model. So now we have some sufficient conditions for identifying psi. Okay. So the technique to identify the psi is actually from showing that the psi and theta in some sense are close. Okay. So the theta is a parameter we just introduced here. So we can show that under certain conditions, the psi and the theta close. Okay. So that's the identifiability of psi. So of course, here to show this result, we need to assume the M to be large. That's why I have this asymptotically identifiability result. So the M goes to infinity. So that's why I have this asymptotics here. Okay. Okay, so let's briefly look at these two conditions. So basically it says if either of the two set of condition holds, then the theta and psi are close. so we can identify psi. Okay, so what are those two conditions? So in the first condition, okay, we say, okay, I have this psi j that is an m-dimensional vector, the m-dimensional vector. So we assume it is kind of sparse. So it's all the L0 norm is little om. Okay, and also for simplicity, we say the k is fixed. So you can relax this. I think you can relax this. So the most important assumption is actually the last one. So this B transpose, this BB transpose is a K by K matrix. Okay, is a K by K matrix. Okay, but B is of dimension K by M. So basically, we assume all the K eigenvalues of BB transpose, okay, are of order M. So this is, if you are familiar with the factor model, so this is a type of pervasiveness assumption. Okay, so they are all spec eigenvalues. Right? Okay, so this is the first set of conditions. So the second set of conditions is the following. So we can do SVD on B. Okay, so this is SVD. And we assume the columns of these right singular vectors, okay, are uniformly distributed over the family of K orthonormal vectors. So in other words, this B space, I mean, by definition, the B must be a orthogonal matrix, right? So basically, this condition says this orthonormal matrix, their direction is random. Okay, it's totally random. Okay, so that's why it's how uniformly distributed. Okay, and also K is little om. So under these conditions, you can also show this result, the asymptotic identifiability result. Okay, so this is how we identify psi from theta. Okay, so in the rest of the talk, so basically we will focus on the estimation of theta because it does not require strong identifiability result. And also if this condition holds, so the estimator of theta is also kind of an estimator of psi, right? Okay. So in the rest of the talk, we will focus on how to estimate theta. So that is our algorithm part. Okay. Okay. So here, let me briefly summarize our algorithm first. So this is actually the most important slide, I would say. Okay. So recall that this is our model. I just rewrite this regression function as theta psi PB plus AB. Okay, and the noise is just use epsilon to denote the noise. Okay, so I have to use the following 3 steps. Okay, so step 1 is I need to estimate the whole matrix. I call this as F. Okay, so I estimate the whole matrix F. So if F is estimated, so I can estimate the covariance of epsilon by the sample covariance. Okay, and we know it has this factor model structure. Okay, so we can do PCA to identify, to estimate the row space of B, or to estimate this projection matrix PB. Okay, okay, so if we can estimate this projection matrix PB, and we will do the last step. Okay, so that is the most essential step. So in the last step, we can say, let's multiply PB complement, say on both sides of these equations. I multiply PB complement here, so I have this. And because theta is already in the PB complement space, so theta times PB complement is still theta, okay? But the key is these 2 terms are all on the row space of B. They are orthogonal to PB complement. So if I time PB complement, so they will cancel out, right? They are all zeros. So essentially, this is latent effect, as we say, okay, these are the effect of X on Y that can be explained by Z, right? Okay, now by doing this projection on PB complement, so we get rid of this hidden effect. Okay, so that is the kind of the most essential step. Okay, and of course I have this error here. Okay, So this is the summary of our algorithm. Of course, there are some technical details, for example, how to estimate F, etc. So I will briefly go through some technical details here. Okay, so the step one, okay, is to estimate this matrix F. Okay, so again, I call this as I group these two together. So I go back to psi. Okay, so I have psi plus L. So the L is just A times B. Okay, so they are of dimension P by M. So to estimate those matrices in high dimension, we have to impose some assumptions like sparsity assumption. Okay, so here we assume psi, okay, is a sparse matrix. So here it actually has some group sparsity. So roughly speaking, you can say if my X is the genotype of genes, so this assumption simply says, okay, I only have at most S genes associated with Y. Okay, so that's typical like a sparsity assumption. Okay, but because they are matrix P by M, so I have to impose some group structure. Okay, so that's more like a group panel, group sparsity assumption. Okay, okay, so this is assumption we make on psi, and also let's say our final estimator is the F hat, which is the sum of psi hat and L hat. So the psi hat and L hat are solved from the following optimization problem. Okay. So if we look at this optimization problem, so we can see the first term is a standard. Okay. And but we do have two extra penalty terms. So this is a group-lasso for psi, and we also have a ridge penalty for L. Okay, because the L is we hope L is generally small or not large. So we add a ridge penalty here. Okay. So if you are familiar with high dimensional like statistical literature, so this type of estimator can be seen as a multivariate lava estimator. So the lava estimator is a combination of penalty, the combination of lasso and ridge penalty. Okay, but those two penalties are imposed on different matrices, so psi and L. So this is different from the elastic net, etc. Okay, so this is different from elastic net. Okay, so you may say, okay, this seems very complicated. How should I solve it in practice? So it turns out it's very easy to solve this problem. So I have the following result. We can say I can simply use the group-lasso approach to solve psi. Okay, so I have psi hat, and then I plug in and solve more like a ridge penalty problem to get L hat. Okay, so you can see it's a very simple procedure to solve this optimization problem. Okay, so I get my psi hat and L hat. Okay, so I can estimate, I can sum these two. So I have F hat. So this is my step one. Okay, so the step two is very simple. I just plug in my F hat. So I get a sample covariance estimate, and I will do the PCA on this sigma hat. So this mu hat k is the top k eigenvectors of sigma hat. So we will talk about how to choose k later. Okay. So for now, let's say, okay, I know k. And the step three, as I said, is the most important one. Okay, but it's mathematically it's very simple. Okay, once you have this PB complement or this estimate, you just use this as a response, treat this as a projected response or a pseudo response, and fit another group-lasso problem to estimate. This is our final estimate of theta. Okay, so the theta tilde. Okay, so this is our whole algorithm. So I think I have some time to go through some theoretical results. Okay, the first theoretical result is about the prediction risk. It's more about the estimator instead. So recall that this is an estimator in step one, and we impose some standard conditions in high dimensional statistics like restrict eigenvalue condition, and we assume W and E errors are all sub-Gaussian. Okay, the standard conditions. And then I have the following prediction risk. Okay, so the xf hat minus xf. Okay. Okay, so in terms of my tuning parameters, so this lambda 2 actually is quite subtle. You will see later. This is penalty for reach. This subtle. But the penalty parameter or tuning parameter for the group-lasso, the lambda 1 is the standard. This square root, the VE, you can treat as a variance in some sense. So it's just the variance over the sample size n. Okay. Okay, so this is a standard kind of choice of tuning parameters in group-lasso type of problem. Okay, so this is the following is our result about prediction. Okay, so here I should emphasize that, okay, when we work on this, for example, this multivariate lava estimator, we don't need to assume psi and L are identifiable. Actually, you get the bound even if psi and L are not identifiable. So it is fun because our goal in this step is to estimate the sum of psi and L rather than the individual component psi or L, right? So we are interested in estimating F, okay, the sum of psi and L, okay? So we don't really care about identifiability in this step. So that's why you have this inf, okay? So this inf over all the combinations of psi and L such that their sum is F, okay? So we have these two errors. So the first, this red part is actually from the reach penalty or reach problem. So this is an error from the lasso. So similarly, you have these three terms, okay? And so the formulas for these three terms are quite complicated. We have that in the paper, but I will show here in this talk, I will show you a simplified formula and some special case. Okay, so you can say what are those three terms. Okay. So the special case I was talking about is orthonormal design. Okay, so we assume we work on the orthonormal design, then it simplifies the analysis a lot. Okay, so under the orthonormal design, we can show that this remainder term 1 is this. So you can say this is essentially the variance of the reach estimator, right? So this is the variance of the reach. You have the P in the numerator. Unfortunately, that's the variance of reach. And the second term is the bias of reach. It depends on the magnitude of this L matrix, okay, the A times B. Okay, so the last term is the rate of the group-lasso. Okay, so that's kind of standard. So first of all, you can, okay, find the optimal trade-off, okay, so this yields the optimal choice of lambda 2, so that minimize the sum of these three terms. So you can find the optimal lambda 2. Okay, so that's why I say this lambda 2, yes, this lambda 2, the tuning parameter for reach is kind of more complicated. Okay, so it depends on those bias, variance, etc. Okay. So also our result can recover the standard rate of group-lasso and ridge regression depending on how you choose lambda 2. Okay. So this is our prediction risk. Okay. Okay, our main result is about estimation or error of theta tilde. Okay, so this is we have another tuning parameter lambda 3. Okay, so so in this result we will introduce two cut points. So one is the lambda 3 tilde. I think the lambda 3 bar. This is a lambda 3 bar. So this lambda 3 bar is the typical choice of tuning parameter in the group-lasso problem, square root m over n. Okay, so this is a typical choice of tuning parameter in group-lasso. Okay, and another quantity is called lambda 3 tilde. Is here. Okay, so lambda 3 tilde. So lambda 3 tilde depends on the psi n. So the psi n is the estimation error of PB hat, right? So if you look at this formulation, so we have this PB hat complement, right? The accuracy of theta tilde will also depend on the error from the PB hat, right? So that's why I have this lambda 3 tilde here, okay? So the final result of the estimation error bound, it depends on the lambda 3 tilde and lambda 3 bar. Okay, so let's focus on these two cases in this slide. So I have two possibilities. So one is lambda 3 bar is larger than lambda 3 tilde. So this basically says my lambda 3 tilde, that's this term, or the estimation error psi n is reasonably small, is sufficiently small. Okay, so if psi n is sufficiently small, so we expect that the rate will recover to the rate of standard group lasso, so which is the case, right? So this is the rate S times square root m over n, right? Okay, so we have this m here because this theta is a matrix, a p by m matrix, right? So we have m dimension. Okay, so that's why I have this square root m in the numerator. But this is already the oracle rate. Okay, so that means this is the rate of the group lasso if we already know the PB. Okay, this if we know this PB, so we have an oracle rate. Okay, so this gray with the oracle rate. So this is a good case, and the following is a bad case. So basically, it says lambda 3 tilde is too large, then the estimation error will be dominated by the psi n, the estimation error from PB hat. Okay. Okay, so again, you may ask, okay, what is the psi n, right? I mean, mathematically, this psi n is again very complicated because the estimation of PB hat depends on those three terms, the estimation error from f hat. So every error will accumulate in this psi n. So it makes the rate very complicated. Again, I will show you a simplified rate. Okay, so this is the simplified rate. So to simplify the rate, we make some extra conditions. For example, the top k eigenvalue of this matrix, okay, are in the order of n. So again, this is a type of pervasiveness assumption in factor model. Okay. So under this condition, we have these two cases, the low dimensional case and the high dimensional case. Okay. So in the low dimensional case, so P is relatively small and S is of order P and capital K is of order M. Okay. And so in the first case, so that basically says M is very large. So it's larger than the order of P. This case means M is fixed, okay? But in both cases, okay, you get consistent result if P is less than the root of square root n. So because we look at the one norm, so this P over square root n is the standard or the best result we can hope. Okay? And it's more interesting to see the result in high dimensional setting. So again, I make some simplification assumptions, okay? And we only focus on the large M. So M is larger than S, the sparsity. Okay. So we get the following rate. So this S over square root n is a standard rate in this type of problem. So the S is the intrinsic dimension, right? So it's S over square root n now, okay? But we do have this red term, okay? So this red term is very subtle. So it depends on the largest eigenvalue of a sample covariance matrix, which can be very large, right? Okay, which can be very large in high dimension. So, but it turns out, okay, if we have the following condition, so the covariance of X has spec eigenvalues. So the X is a p by 1 vector. So if the covariance X has some eigenvalue of order P, okay, so in that case, you can also show that the sigma 1 is also of order P. Okay, so you have P in the numerator. That seems horrible, but okay, the result we can show that is this L matrix. Okay, their Frobenius norm is very small. So you can show this square, the square of this Frobenius norm of M of L over M is of order 1 over P. So if you put this here and do some math, you can see this red part is exactly capital 1. So you recover this the standard, the ideal rate or the oracle rate. Okay. So why this L can be small? So again, if we go back to our definitions, the L is A times B, right? So the A matrix, where is that? So the A matrix has covariance X inverse here. So if covariance X has sparse eigenvalues, so this guy can be small. Okay, so this is why we can show L is actually small. Okay, so in this sense, we get very good result if P is very large. So we can treat this as a plus of dimensionality of P. So of course, M is also in the denominator. So if M is large, so it also helps. Okay, I would say it also helps. Okay, so it's kind of double plus of dimensionality in terms of M and P. Okay, I don't think I have time to talk about the heteroscedastic case. So I will briefly mention how to choose K. So the way we choose K is from this factor model literature. So we use the so-called eigenvalue ratio approach. So basically, if we look at the eigenvalues of the sample covariance matrix, we take the ratio of adjacent eigenvalues. So the largest one would be our K hat, right? So the reason is this matrix should have K eigenvalues ideally. So if you look at J equals K, so K plus 1 eigenvalues of this matrix, it should be very small, close to 0. So if something divided by a small value, it should blow up, right? So that's why, okay, we choose the argmax of the ratio, okay? So we have also some theoretical guarantees for this K hat in the paper, okay? But I skipped the theory here. So let me briefly show you some numerical results. So we consider the following simulation setting. So 3 latent variables, sparsity is 3, and we generate X from a multivariate normal. So we use this model to generate a latent variable. So this eta, in some sense, characterize the dependence or strength of dependence between X and Z. So if eta is large, that means the latent variable are more dependent on X. So it's become more difficult to deal with this case in some sense. Okay. And this is a homogeneous noise. This is a heterogeneous noise. For the heterogeneous noise, I use the parameter alpha. So the larger alpha means the errors are more heterogeneous. Okay, the errors are more heterogeneous. Okay, so I compare a few methods. Okay, so basically we have this oracle method. We use a true matrix B, okay, PB. And also we consider some group-lasso or range, okay, etc. So these are basically the method. We just pretend there's no hidden variables, and also possibly a least square. Okay. Okay, so let me show you the result. So this is the estimation error, okay, and the homogeneous case. So this is a PM, P and M, P and M, okay. So here in this, for example, if you look at this plot, we can say the oracle, this black one, has the smallest error that's expected, right? Okay. And these two curves are the HIVE, our estimator, and the so-called HIVE, the HIVE for the heteroscedastic noise. Okay, so they all perform equally well. Okay, but if you look at some, say, lasso, this purple, and orange, the blue one. Okay, so this purple line, so you can say the performance become worse if eta become larger. That means that these hidden variables are more and more important or correlated with X. Okay. So this is what happens for the homogeneous noise. For the heterogeneous noise, you get some similar results. Okay, but in this case, the HIVE, the heteroscedastic version of HIVE works best, okay, because it's designed to deal with this heterogeneous noise. Okay. Okay, so another interesting result is the following prediction error. Okay, so this basically look at the first step, the F hat, the estimation error or prediction error in the F hat. Okay, now I only focus on the homogeneous case. I compare this lava type of estimator with the lasso and the ridge. Okay, so you can say even if I have a very small eta, you can say even if I have a very small eta, in that this hidden variable can be ignored in some sense, right? So those lava type of estimator, okay, is almost as good as this lasso, or I think they are equally good. Okay, And also, if eta gets larger, that means the hidden variable become more and more important or informative. Then, okay, all those ridge and lasso become worse and worse. But our estimator still has very good performance. Okay. So when I say work on this simulation, I think it's kind of surprising because I would expect that so this type of lava plus this type of ridge plus lasso type of approach may have worse behavior if the, for example, hidden variable is small. So in this case, the lasso would be ideal, right? Because we have a sparse matrix. When you estimate the sparse matrix by lasso, that should be the best way we should do that. But it turns out this ridge plus lasso approach almost does not lose anything. So I'm very surprised to see this result, but okay, at least you can see it has very good performance across the whole range of eta. Okay, so let me wrap up the talk. Okay, so in this talk, we consider this multivariate response model with hidden variables. So we studied the identifiability of the regression parameter, and we developed a HIVE algorithm, okay, or HIVE algorithm for the method. And also we show some statistical guarantees. So current work we are working on is how to do the inference on the parameter per se. Okay, so that's all for my talk. Okay, thank you.
Thank you, Yang, for the presentation. That's very interesting. So now we open to questions.
I have a question. So this is a really nice presentation. I love the whole framework and your methodology as well as the rigorous theory. And I have a question when you introduce the linear structure equation model. Yeah, so essentially, like you have you assume the X is induced by Z, right?
Mm-hmm.
And
right.
But later on, you feel that these two, Z and X, they are kind of correlated. That enables you to establish the relationship between the hidden variable and the covariance. And my question is, what if the Z is not fully captured by the X?
So for example, in these two models, so basically you have to assume, for example, X is a cause of Z. So in other words, if you write it this model, they would say, okay, the W, the error, and X, they are independent. Okay, they are independent. Similarly, this gamma and Z, they are independent. So, but in our method, we have this projection. So in some sense, I have a kind of equation similar, but there's a very subtle difference because this I do not need this W and X to be independent, right? So this W and X, by definition, they are uncorrelated, but they will not be independent. If you assume they are independent, in some sense, you assume this is a kind of a true model in some sense, right? This is a model, but here we just say, okay, this is just through a L2 projection. Okay, so I have this A times X, and I have a residual term. I call this a W. So these two parts are not necessarily independent. And indeed, I think in this paper, this confounding variable model paper, so their idea is to say, if I know X, I can treat this as a factor model for X. So I can essentially estimate all my hidden variables Z. So this is something kind of something that has been used recently to deal with, for example, the multiple cause. Okay, so there is a paper by David Bly, so and also I think his student, so the Bly's of multiple cause. So in assume these factor models, so they can use their observed multiple cause to recover, okay, or to recover, I mean, asymptotically, to recover the hidden variable Z. Okay. But this is different from what we did here. I mean, for example, if you take this model as a true model and you rewrite it, and you rewrite it in this way, you flip X and Z, and you say, what is a W in this case? So actually, from this confounding variable model, you can show the W here is actually a very small matrix. So some Frobenius norm, they should be 0 or something, or approach 0. So it's a very small matrix, W. But this is different from our assumption. For example, here we have the covariant W that has full rank, and also we have some pervasive assumption together with the W. Okay, so in some sense, we do not really say our latent variable can be exactly recovered by the X. Okay, so this is different from that, like multiple calls, the paper on multiple calls, etc., or the confounding variable model. So there's some subtle difference. So yes, because recently we're working on the inference paper, so I realized this is actually a very essential difference between these two different methods. Yes.
Thank you. Thank you. Yeah, it's cool.
Yes, welcome.
I'm curious about how you interpret the theta in the deck you showed us.
So I'm not sure what is a good way to interpret the theta. So I think I call this as here as a partial direct effect. Okay, so this is I guess in some sense this per se is more like a direct causal effect in this DAG structure if you have some mediator variables. So what I can say is theta is a part of the per se. So we call this as partial direct causal effect, but I'm not sure whether there's a better name or maybe there's something similar in the causal inference literature. So I'm not super familiar with those literature. So maybe there's something there.
Okay. I have also another question. So you don't necessarily assume X and Z are linearly dependent, right? But in your simulation study, you assume.
Yes, in the simulation, I just assume generate Z from X model, right? So it's here, I generate Z from this X. And I'm not sure whether we did more simulation to use different models. So yeah, probably we should try some different models for X and Z. So they have some nonlinear dependent structure and see how it works. Yes.
Okay. Yeah. Also, you have so many tuning parameters.
Right. So I think we have 3 tuning parameters. So there's here lambda 1, lambda 2, and also there's lambda 3 here. Yes.
So in practice, how do you choose
let me say, I think for this lambda 1 and lambda 2, let me say, here we should use kind of a 2 grid for lambda 1 and lambda 2 to search the grid jointly to use cross-validation. So because this one also depends on lambda 2, right? Okay, so this is lambda 2, this is lambda 1. So I think we have cross-validation to tune lambda 1 and lambda 2 jointly. So once we do that, so we would have a f hat, then we can tune lambda 3 separately. So because lambda 1 and lambda 2 are kind of entangled together, but lambda 3 is something here. So it does not depend on the lambda 1 and lambda 2. So once you have this estimate, you can tune lambda 3 to get a good estimate of theta tilde. Yes, I think this is how we did that in the yeah.
Okay, thank you.
Okay, yeah.
Other questions for Yang? it's right on 4 o'clock, so we may stop here. And I thank Yang again for this wonderful
Okay,
talk.
yes, thanks for having me here. Yes, yeah. So we will see each other in some conference. Hopefully next year the conference would be in person. Yeah.
Right.
Yeah, I don't know for GSM or like INA if it is feasible or not.
Let's hope for the best.
Yes. Okay, yes. Thank you guys. Yes.